So let's keep on continue discussing our complex number in modular arithmetic and the Fermat's Christmas theorem. So how to prove this? Um, we first the prove this direction, which is p if there exists a p that sorry I will write it better if there exists a p that p divides x squared plus 1 we can it implies that p is congruent to 1 mod 4. um let's write this in the modular arithmetic form like this, right? And sorry, it is like this, right? Um, and we can have some um think about this. This is negative one, and we have another theorem that is highly related to this. It's very similar. Is the Fermat's little theorem, right? If I write this out, can you see anything we can do here? Yeah. If you think about this form, we can try to mix this condition into here. We know p is a prime, and p minus one should be an even number, and we can thus get a two out, and like this, and because if we mod p, we can have x squared is equal to minus 1. Um, and this is very good because this has to be equal to 1 mod p. And if this minus 1 to the power of 2 of this is equal is congruent to to positive 1, it means that p minus 1 divided 2 should be an even number, right? Or we write this as 2k. 2k implies an even number, and we directly can show that p is equal to 4k plus 1 with some algebra manipulation. And we finish our proof in this side. And another side is we need to show that here we need to show that another side is when p is congruent to 1 mod 4, we can deduce p divides x squared plus 1. There exists some x that p divides x squared plus 1. And how to do this? The thing is, we need to we need to construct some x, right? If we can construct an x, we prove there exists statement. Maybe it's better to write it as a modular arithmetic form. You can see it better. And if you think about this, if you see sometimes there exists a minus 1 here, and there it is modular p. Do you think of any theorem that is useful similar to this to this expression? Yes. The famous Waltham theorem, right? P minus 1 factorial is congruent to negative 1 mod p. It's essentially the same in the right hand side. So we think that if it is possible to construct an x that maybe x squared is congruent to p minus 1 factorial or something related to this, and we finally get minus 1. So how do we construct an x? A way is because p minus 1 is an even number, right? You can think about, because for example p minus 1, for example, if it's 6. You see, if I write down 6 times 5 times 4 times 3 times 2 times 1. This is exactly congruent to -1 times -2 times -3 times 3 times 2 times 1. And this is something we think that the two, we can combine the two and get some kind of square, right? Here's the square, and that's very nice. So what we construct X is we use the factorial, like this factorial, which is a half of p minus 1. And in this sense, if we square x, we can write it out, right? Expand it, and there's two expression, right? All over to 1, and another expression is the same. But we know that in the previous observation, we know that we can use p to minus this every term here, and we know that p minus this is equal to negative p plus 1/2. And this is also similar when we use p minus 2 over p minus 3 is equal to negative p plus 3 over 2. And it is very nice because we can finally get factorial here. Because this end in the half, and we link the two together, and here is how we do this, and we can write it as a more clear way here, and this is equal to negative 2 over p plus 1, negative 2 p plus 2, p plus 3, negative 2 p plus 5, all over to negative p minus 1, right? You can check it better yourself. And we know this here, it ends at 1. And here's the thing, we know there's how many minus here? There is minus 1. There is exactly p minus 1 divided 2 minus sign here. And the thing left is p minus 1 factorial. And according to Wilson's theorem, this is exactly p minus 1 factorial is minus 1, right? Mod p. Therefore, we got x squared is congruent to p 2 over p plus 1, 2 over p plus 1. And this should be negative 1, right? Because we want to construct an x such that x squared is equal to negative 1, which is a complex numbers condition. If this has to be negative 1, 2 over p plus 1 should be an odd number, right? Should be 2k plus 1, right? And p plus 1 is equal to 4k plus 2, and p is equal to 4k plus 1, which completes our proof of the Fermat's Christmas theorem. And we finish our proof altogether. There is another, and if you reflect on this construction, it's a little bit hard to think of, because yeah, indeed, if you try to write it as like that, it's kind of easy to relate to Wilson's theorem, and you should always keep Wilson's theorem in mind. And we know on the other hand, the other way is proved by Fermat's little theorem, right? You should also always keep those important theorems in head. And yes, and this is how we prove. But generally, we have we have an easier proof that is at least easier to think about when we learn order in the future in the next video. And after learning order, we will come back and prove the Christmas theorem again. And yes, that's today's video, and thank you for your watching.